What happens when an AI remembers too much? The real danger is its perfect memory. From leaking private chats to plagiarizing books, hoarding data is a massive liability. Today, we're breaking down the memorization dilemma and why traditional benchmarks fail. But there's a solution: the HUBBLE Suite, a revolutionary open-source framework for AI memory management. We'll show you how to hunt leaks with tracers and sanitize outputs with the Dilution Solution. Master the timing trick to understand AI unlearning. We can finally build models that are both powerful and privacy first. If you're a developer, researcher, or care about secure AI, you need to see this. Let's dive in.
Welcome to this explainer. Okay, today we're setting out on a super fascinating investigation into the actual mind of artificial intelligence. We're zeroing in on large language models to ask a question that's literally been keeping researchers and tech companies up at night. How do these massive systems actually memorize the data they're trained on? For a long time, it's just been this impenetrable black box. But today, we're prying it open. We'll be unpacking a groundbreaking scientific study centered around something called the HUBBLE Suite.
So, to understand why this is absolutely crucial, think about this for a second. What happens when an AI remembers a little too much? I mean, we've all seen the incredible, mind-blowing things AI can do, right? But the stakes are incredibly high when an AI accidentally spits out a snippet of someone's totally private email, or, say, recites pages from a copyrighted book completely verbatim. It's a huge problem, and fixing it? Well, that requires us to understand exactly how that memory is formed in the first place.
Here's our roadmap for today. First, we'll unpack the memorization dilemma. Then we'll meet the HUBBLE Suite and check out how researchers went about injecting tracers. After that, we'll hit the core findings. Finding 1, the dilution solution, and finding 2, the timing trick. Finally, we'll wrap up with the future of unlearning.
Let's dive right into Section 1, the memorization dilemma.
Before we get to any solutions, we really need to define the stakes here. Researchers call these memorization risks. Basically, these are deployment threats that pop up when large language models essentially regurgitate their training data. And we're talking about real, tangible, real-world problems here. Things like copyright infringement, where a model outputs protected works, or privacy leakage, which is a big one. That's where sensitive, personal info gets exposed. And then there's test set contamination, which is basically when a model cheats on its evaluations because, well, it's already seen the answers during training.
But, the reality is that AI memory isn't purely evil. It's a classic double-edged sword. On one hand, you have factual knowledge. That's the good stuff. Memorizing facts is exactly what helps these models perform well, answer your questions accurately, and just be useful. But on the flip side, you have those deployment risks we just talked about, leaking personal info or plagiarizing protected works. That's the bad. So the ultimate challenge is figuring out how to keep the good memory while totally eliminating the bad.
Which brings us right to our solution space. Section 2, meet the HUBBLE Suite.
And this ambition is captured so perfectly by the official HUBBLE Model Suite mission patch. The researchers specifically named it HUBBLE because, just like the Space Telescope, it's designed to peer deep into the unknown, in this case, the AI cosmos. It's actually a suite of fully open-source large language models built specifically for the scientific, rigorous study of AI memorization. It's a real game changer. To actually see into that black box, they set up this brilliantly clever experiment. They trained 2 distinct types of models. First up, the standard models. These were pre-trained normally on a massive, massive corpus of up to 500 billion tokens. You can think of tokens as basically fragments of words, all English text. This was their control group. Then you have the perturbed models. Now these were trained the exact same way, but with a twist. The researchers did controlled insertions of sensitive texts. If you want a good way to picture this, think of these perturbed models like patients who've just been injected with radioactive dye, so the doctor can precisely trace their blood flow.
That leads us nicely into Section 3, injecting the tracers.
So what exactly were they injecting into the network? Well, you can kind of frame these data sets as characters in a detective story. For copyright risks, they actually fed the model passages from both popular and unpopular books, plus a bunch of Wikipedia articles. To test privacy, they injected biographies from the Yago knowledge base, and get this, secret chat logs with specifically assigned usernames. And finally, for test set contamination, they threw in standard benchmark answers, like from the MMLU test sets. They were feeding the model all these specific little characters just to see exactly what it would eventually spit back out.
But here's the thing. They didn't just insert them once.
To casually track exactly how repetition builds an AI's memory, these text tracers were duplicated at totally different rates. Some were inserted 0 times, just to act as a baseline control. Others were inserted once, or 4 times, 16 times, scaling all the way up to 256 times. That 256 mark represents maximum exposure. By doing this, they could measure the exact number of duplicates it literally takes for a model to truly, deeply memorize a piece of text.
And the results here, honestly, they were staggering. Check out this wildly surprising fact. Just one single instance of test set contamination can cause memorization. Just one. These networks are incredibly wildly sensitive. But crucially, and this is a big but, seeing that test answer just once didn't actually improve the model's true capability to generalize and answer unseen examples. Nope, it literally just memorized the cheat sheet.
Okay, let's look at the major breakthroughs, starting with Section 4, Finding 1, the Dilution Solution. I want you to just consider this question for a second. What happens if a password appears just once in a really small data set versus appearing once in a totally massive one? Intuitively, right, in a smaller data set, that one password stands out like a sore thumb. But in a massive data set, it gets completely buried. This whole idea boils down to the frequency of the data relative to the sheer scale of the dataset itself.
And this experiment proved that exact intuition. The researchers compared models trained on a 100 billion token corpus against models trained on a 500 billion token corpus. The finding? For the exact same piece of sensitive data, duplicated the exact same number of times, that larger 500 billion token corpus diluted the sensitive data. It significantly reduced the memorization risk. So here is our first golden rule. You can effectively wash out or dilute sensitive data by simply increasing the sheer size of the surrounding training corpus.
But wait, there is a catch. We have to balance that dilution effect with the actual size of the model itself. The data shows that larger models, like their 8 billion parameter model, are just way better at memorizing than the smaller 1 billion parameter models. You can think of parameters kind of like the neural connections in the AI's brain. As these models scale up in size and complexity, the risk of memorization scales up right alongside it. It basically means that while dilution is necessary, it's this constant, ongoing battle against the model's growing capacity to remember things.
Let's move right along to our second major finding. Section 5, Finding 2, the timing trick.
So this finding focuses not on how much data there is, but when it's actually shown to the model. The researchers ran this really clever series of timeline experiments. Instead of just scattering those tracers randomly throughout the entire training process, they only injected them during very specific pre-training windows. Basically, they chopped the training timeline into quarters. The first 25% of training tokens, the second quarter, the third, and then that final 25% stretch.
And the crucial takeaway here is fascinating. They discovered that inserting sensitive data really early in the training process actually allows the model to just forget it. Conversely, if you inject that exact same data in the final 25% of training, it drastically increases the risk that someone could extract it later. By withholding continued exposure to that sensitive info as training goes on, you're actually providing a natural form of privacy. And that gives us our second golden rule. If you absolutely have sensitive data you must use, order it so it appears earliest in the training run. Give the AI time to naturally forget it.
Let's pivot to our final topic today, Section 6, the future of unlearning.
Before we completely wrap up, I just have to share this amazing little twist from the study. Because you might be sitting there thinking, well, hey, I'll just change the wording of my private data before I train the model, right? Wrong. The researchers proved that paraphrased text can still be memorized. They trained models on paraphrased biographies, and guess what? The AI could still reconstruct the private information. It turns out these models don't just mindlessly memorize exact strings of text, they build this deep underlying semantic memory that lets them infer private info even if the exact words are completely changed. It just goes to show how incredibly complex the challenge of making an AI actually unlearn something really is.
Now, the HUBBLE Suite isn't just some one-off academic study. It's having a massive, lasting impact on AI safety research because the researchers openly released it and perfectly randomized those data insertions. It acts as the exact ideal sandbox developers need right now. It is a perfect testbed for studying membership inference attacks, which basically means trying to figure out if a specific piece of data was lurking in the training set. It also provides this tightly controlled environment for researching machine unlearning methods to force an AI to forget. And ultimately, understanding all these mechanics helps establish legal safe harbors for copyright law, which gives everyone clear guidelines on what training practices are actually fair and safe.
To bring this whole thing full circle, the researchers wrote this in their paper. We hope our models open new scientific frontiers in the spirit of the Hubble Space Telescope. And honestly, they really hit the nail on the head. They've given the entire scientific community this absolutely vital tool to peer deep into the inner workings of AI memory, bringing real light to what was previously just a dark black box.
I want to leave you with one final thought to ponder today. As AI becomes more and more deeply integrated into our daily lives, learning from this vast, endless ocean of human data, how should we balance an AI's fundamental need for memory to actually be useful with our very human right to be forgotten? It's a hugely complex frontier, for sure, but thanks to groundbreaking tools like Hubble, we are finally equipped to start navigating it. Thanks so much for joining me on this explainer, and remember to keep questioning the technology around you.